Yeah.
Don't worry about it.
Okay, so it's getting a little dark. Okay, we're gonna try. So we'll go through this material. So the next lecture will be an online lecture capture. Okay, and we'll just watch it. Okay. Alrighty. Yes? Okay. So we were talking about this last time. We talked about the Nernst equation, right? Can anyone remember, just a little recap, what does the Nernst equation actually tell you? Or what does it measure? Yep. Okay, membrane potential, right? Or voltage of that cell with a particular ion. Like where is a particular ion in equilibrium? Where does the voltage have to be for that particular ion, like potassium or sodium, to be in equilibrium? And so I sort of worked out, we went over potassium and sodium, and this is just showing how we calculate that. This is written a little weird, so if we were to do it for like potassium, we would say EK is equal to, there's a constant here, these constants that we basically put in the numbers and I get about a 62. This is like rate, temperature, Faraday constant. It's all the sort of constants to plug in and calculate this. So I would just say 62, and then basically all of this comes down to, there's the valence of that particular ion, right? So the charge of that particular ion. And in the case of potassium, what kind of charge does it have? 1, right? Plus 1. So it's over 1. And then it's times the log, and in this case, it's the ion, K. How much concentration of K is on the outside versus what's the concentration of K on the inside? Okay? Just did it right there. That is the Nernst equation. So if you know what's the concentration of potassium outside of the cell, what's the concentration of potassium inside of the cell, you plug in, and actually here they are right here. Outside 5, inside 140. You can plug that in right there. Sorry, I did that the opposite, what I was trying to do. 5, 140. So if you multiply 62 divided by 1 times the log of 5 divided by 140, you'll get a number. What is that number? There you go. Negative 90. What are the units? Yes. Voltage or membrane potential is always in millivolts, right? That is just saying, at this concentration maintained right here, the voltage of that cell would be minus 90. So if potassium is allowed to do what it wants to do and stay in equilibrium, that cell is going to have a membrane potential of minus 90. We can do the same thing for sodium and plug in sodium, right? Outside sodium, 150, over inside sodium, 15. Plug and chug, you'll get a number. What is it for sodium? Right, positive or plus 62, somewhere around there. Okay, and whatever this big fat hairy one, this Goldman-Hodgman-Katz equation, and this is just saying, well, we don't just care about one ion or another ion. All of those ions together in sum determine what is the voltage of that cell. So they worked this out and went, okay, this is how you do it. You factor in chloride, sodium, potassium, and that is going to give you the voltage or the membrane potential of that given cell, knowing those concentrations. All right, so going into this a little bit more and how this is going to affect action potentials. Potassium equilibrium potential is something we call the EK with a little subscript K, like that. That's the potassium equilibrium potential. That electrical attraction, remember there's a lot of negative ions inside the cell, that would pull, draw potassium into the cell until it reaches that point where the concentration gradient drawing potassium out, right, because it's going downhill, it wants to leave because it's high inside, versus the attraction sucking it in is going to be in equilibrium. It's going to be exactly in balance. And where does that happen? That happens at minus 90 millivolts, okay? So potassium would reach this equilibrium with more potassium inside than outside. Normal cells, of course, have 140 millimolar potassium and 5 millimolar potassium outside. So higher potassium inside, lower potassium outside. There are a few numbers in these lecture series, like membrane potential and action potentials, where you have to remember the numbers. I want you to know the Nernst equation, for sure, and I want you to know these numbers. What are the concentrations of potassium, sodium, on the inside and outside of the cell? So you have to know those. Because if you need to plug them in and figure it out or know what a standard neuron has, based on the concentrations, you need to know that. All right, So that's what we sort of were going over. This, I spelled these out, that first slide that has all the equations and beakers and stuff going on. This kind of steps through exactly those different processes. So that resulting difference in membrane potential or voltage is the EK, right? The equilibrium potential for potassium, and that's minus 90. So it means the inside has a voltage 90 millivolts lower than the outside. That's it. So basically, another way of saying this same thing is that that's the voltage of that cell needed to maintain that 140 inside and that 5 outside of the cell. Yes? Okay, a little bit of numbers here. So sodium, of course, is also important for establishing the resting membrane potential, or membrane potential in general. Sodium concentration in a normal cell is somewhere around 15 millimolar inside and about 150 millimolar outside, so exactly the reverse of potassium. But you already knew this, right? Maybe not the exact numbers, but you already knew sodium is high outside and it's low inside. Potassium is high inside and low outside. Remember? Would I give you a little way to remember that?
You don't want to be salty.
You don't want to be salty. We don't like salty people. You don't want to be salty. High sodium outside, low inside. Potassium is the reverse of that. So to keep that much sodium out, the inside would have to be positive to repel it, to prevent that. So to maintain that gradient, that difference in sodium, the cell actually has to have an ENA that's positive. And actually, based on the concentrations you use, because this can vary a little bit depending on cell or tissue type, but if we plug those in, it's about plus 66 millivolts using those numbers, okay, or similar numbers to low inside, high outside. Here's that equation just written out in an easy way, spelling out what those different components or factors are. So to calculate equilibrium potentials using the Nernst, we set it up like that. And this is the constant, 61 or 62, it's that RT over F, right? This rate has to be divided by the valence or the charge of that particular ion. So if you're working, charge is important, right? Pluses and minuses, that's what's helping to set up the membrane potential. So if we're working with something like chloride, that would be a -1 right there, yes? If we're working with something with potassium or sodium with a positive charge, that's a 1. So basically, it's the equilibrium potential is equal to that rate constant divided by the charge of the ion times the log of the concentration of the outside of that ion, concentration inside of that particular ion. So equilibrium potential, XO is the outside concentration of the ion outside of the cell, XI is the ion concentration inside of that particular cell, Z is the valence or the charge for that ion. So that's it. You have to know the equation. I'm going to ask you that equation. Or to plug it in, right? To know it, give you some concentrations and say, tell me what the equilibrium potential would be for this particular ion. And you have to, okay, plug it in so you can calculate what that is. All right, so ion channels are really, really important. So in firing an action potential, how a cell actually fires, it uses ion channels, okay? So membrane potential, how it's set up, resting membrane potential, relies on the sodium, potassium, ATPase, right, maintaining those gradients. But then when a neuron actually gets the signal or the stimulus to fire, there's going to be opening and closing of different ion channels, so they're really important. So here's the outside of the cell, here's the inside of the cell. These are supposed to represent that sodium, potassium, ATPase pump, kicking the sodium out, bringing the potassium in. It's maintaining that nice concentration gradient. This is supposed to represent the potassium channel, this is the sodium channel. So for any of these to happen, and this is just, we're going to be talking about action potentials and how a cell fires. If a cell is going to open something like a sodium channel, so we'll focus on the sodium channel for a second. Where is sodium going to go if those ion channels pop open? Think about facilitated diffusion. We talked about ion channels and gates and carriers and all that stuff. If I have a channel and it opens, where is sodium going to go? If it's specific to sodium. All you have to know in this case is where is sodium high, where is sodium low. Facilitated diffusion allows diffusion through a pore, or through a channel.
It goes to the cell, which is a lower concentration.
Into the cell because there's a lower concentration in the cell. And fast. If I open sodium channels, depending on how many sodium ion channels I open, that sodium is so high and salty on the outside of the cell, those ion channels pop open, sodium is going to just flood right into the cell. Fast. Now what happens if sodium rushes into the cell? What does that do to the charge of that cell? Or the membrane potential of that cell?
Positive.
It's positive, it makes it more positive. Okay. So now if you look at the potassium ion channel, What happens if we open a potassium channel, or a bunch of them? Where's potassium gonna go? It's gonna leave the cell, it's gonna rush outside, right? What's that gonna do to the membrane potential if I lose all the potassium from a cell? More negative. It's going to become more negative. So its membrane potential is going to drop. You see what you just did is you sort of described what happens when a neuron fires. That's exactly what happens when a neuron fires. It's deviating away from membrane potential. It's firing. Okay? And it happens through ion channels. So we're going to look at exactly the steps that do that. But you always have to go back to what I told you. Like, you don't want to be salty. It always goes back to that. High salt, high sodium outside, low inside. High potassium inside, low potassium outside. If you remember that, and then you remember which ion channels open, then you'll know, oh yeah, sodium rushes in. Oh yeah, those open, potassium rushes out. So basically the neuron trace, so when you press on the back, make sure that that's working and like it's, yes, okay. All right, so if I draw a neuron trace, we can do this with an oscilloscope, right? Put in our little electrodes inside, outside the cell, very precise, accurate measurements. We can get charge differences. We can measure voltage, right? So we can do voltage, or I'll call it membrane potential of the cell on the y-axis, and this is in millivolts. Just do that, and this is over time. I'm going to do some numbers on here. We're going to go 30 is kind of our upper range. We're going to have a 0. Down here, this is not totally the scale, but we're going to start around minus 70. Why am I starting around minus 70?
That's the resting membrane potential?
Yes, for most cells and most neurons, it's resting membrane potential, or RMP. So cells, based on their charge, based on their electrochemical gradients of ions, that's where they sit. That's where they're happy. So if we go here, we're sitting right about there. That's resting membrane potential. Okay, make sure I have the colors. All right, so I'm going to add to this piece by piece, because I feel like if I do it slower and systematic, you'll get it a little bit better. So changes in membrane potential are going to change charge in the cell, right? Changes in membrane potential, or ions coming in or out, clearly that's going to make a difference right here. The cell is not going to be able to maintain RMP when ion channels are going to open and close. So this brings us to ion gating. What does gating mean? So we have ion channels. Some ion channels are always open. They're like leak channels, and a little bit of ions go through, and some have to be popped open by different stimuli. So what does it mean if an ion channel is gated? If I say, well, this ion channel is gated. Right, it's closed, it only opens at certain times. It's like a gate to your house, right? No, you can't come in, sorry, it's COVID precautions, go away. That wasn't funny, maybe. Okay, but it's not gonna always be open. I have to like let it open, then they're gonna come through and I go, we're closing it, it's gated. So ion channels, the core principle of how they work with action potentials, they are gated. They're not always open. So they're controlling basically what happens here. So changes in membrane potential are controlled by changes in the flow of ions through channels. And those channels are very specific ion channels that are gated. That means they only open in response to certain stimuli. We'll look at what those stimuli are right now. Potassium has two types of channels. You have to know what those channels are, okay? One is a leak channel. That means they're there in the membrane, they're not gated. That fence is always open. So potassium can kind of leak through gradually, okay? Not gated, always open, they're called potassium leak channels. The ones that are gated are called voltage-gated potassium channels, and those are really important for a neuron being able to talk or fire, okay? So when a particular membrane potential is reached, in this case, voltage-gated means that gate opens, that core of that ion channel opens and the gate swings open only at a certain voltage, okay? So some ion channels, they can bind to different things and they pop open. These are specifically gated by voltage. So that means all the membrane potential has to do is change to a different voltage, and the conformation, it seems like magic, really. It seems how neurons fire and all this work. I used to, as an undergrad, I used to just think it was magic. It made no sense to me. Like, how does it know? I would always say, like, how does it know? How does this know? How does it just, but how it happens is voltage changes, the ion channel changes shape. It swivels in the membrane opens up the pore, so now potassium can actually rush out. Okay, so it's not just based on voltage, so it causes changes in the actual molecule, in the ion channel itself. So they're closed at resting membrane potential, and then when the cell reaches a certain voltage, it pops open those voltage sensitive or voltage gated potassium channels. Sodium, of course, is very important in all of this, arguably more important even, but all these things in combination are important, they go together. Sodium only has voltage gated sodium channels, no leak channels. So remember in the beginning I said membrane potential, it's set up by the sodium potassium ATPase, right? And the membrane is more permeable to potassium than anything else. So the cell sits at a minus 70. What is the equilibrium potential for potassium? Think for a second.
Minus 90.
Minus 90. Is that far away from that? No, it's not. There's leak channels, so potassium can actually do what it wants a little bit. It gets pumped in, and then it can diffuse out through the leak channel. So potassium and the NAK ATPase are sort of maintaining that membrane potential at that very negative millivolt, okay? So sodium channels only open by voltage. There's no sodium leak channels, okay? So the cell sits, or the neurons sit at a very negative membrane potential. Membrane is less permeable to sodium. When I say the membrane is less permeable, when we talk about ions, how are ions getting through a membrane? Are they ever just going to slip through the phospholipid bilayer? No, they're not. So if I talk about ion permeability through a membrane, that means I'm talking about ion channels. The ion channels are either open all the time, or they're shut, or there's some combination, but they have to be going through specific ion channels, okay? So in this case, voltage will determine if there's a change in membrane potential, it'll open, potassium will rush out. Gets past that voltage, or approaches a new voltage, then it shuts and it deactivates, closes and then deactivates, so it can't reopen again. And then it closes until the next wave or stimulus. All right, so if you alter membrane potential, we say that those cells are excitable. And almost many of the important cells of your body, neurons in the brain and the spinal cord, the peripheral nervous system, neurons in your eyeballs, your ears, your nose, your mouth, all the special senses, your muscles, all your skeletal muscles, your pancreas that dumps out insulin, they all can fire an action potential. They all change their membrane potential. So they change their charge. They actually veer away from resting membrane potential, and that's how they do what they do. So we call them excitable, or they have excitability. It's where they change their membrane potential. And simply that'll change a lot of their activities and their communication with other cells and what they're able to do. So it's caused by changes in permeability to certain ions. That means opening and closing of ion channels. That's how all of that happens. It's not magic. It almost seems like it's magic, but it's not. That's the principle of physics of how it happens. So ions follow their electrochemical gradient. Remember, this is the combination of the gradient, so the concentration difference on either side of the membrane, and their attraction to opposite charges. Positive goes with negative. Okay, so these two things determine where those ions are going to go. Electrochemical gradient, attraction and concentration. That's going to determine where they fly in or out. Flow of those ions we call ion currents. Just like in a battery or in electrical wires, electricity, these cells are electrical, they're excitable. Charges flow. So if we have ions moving, we call those currents, ion currents. And it literally makes the zip that goes down neurons when they fire an action potential or an impulse. So this occurs in limited areas where there's ion channels located on that plasma membrane. Now maybe I should draw the actual neuron. Okay, so we've got a cell body, right? And then all these dendrites that sort of come out. We've got the little base of the cell body, or the axon hillock, that gives rise to the axon. And then it diverges out and sends all these little axon terminals or branches out at the distal end with these little swellings. These are highly exaggerated. Boutons or feet.
Professor?
Yes?
It's on the screen.
It's
on
what?
the screen. It's on the screen. It's on the screen. It's not
You can't see the.
Yeah.
Oh, I'm out of the range.
Yeah.
Can you stop that just a little bit? Thank you, I got some videography help. Okay, so we got the typical neuron structure, right? You guys have all learned this at one point or another, I'm sure. There's little, basically cells that wrap around like pancakes, and they've got fat in them, little lipoprotein myelin, and they wrap around in these layers, and they insulate, almost like cable casing, around the axon, right? There's patches of membrane that are exposed, that are not covered by this fatty myelin wrapper of these specific cells that help this neuron function. So in these areas right here, I'll zoom in green. Just gonna put a bunch of little boxes. These are ion channels, okay? We'll do a couple different types, because I'll just insert 2 colors. So just add, there's a few different types here. We're gonna go over what they do, but the point is they're all clustered right there. They're in those gaps. You guys remember ever learning this? What are those gaps called? Nodes of something. It's in the lecture slides too. Yes, nodes of something. Yes. Nodes of Ranvier. Looks like Ranvier, it's a French guy who worked this out. Nodes of Ranvier. That's where we find ion channels clustered at these nodes along the axon. Okay, we're looking at the axon. These are the axon terminals. These are the boutons, looks like buttons, spelled like buttons, but we say boutons, little swellings at the end. This is where there's all these little synaptic vesicles ready to go, sort of some docked, some stored. Guess what's in these little synaptic vesicles at the end of these axon terminals?
Ions.
Not ions.
Neurotransmitters.
What?
Neurotransmitters.
Neurotransmitters. The chemicals that allow one neuron, when it fires an action potential and it reaches the bottom, to dump out its neurotransmitter. How does it dump out its neurotransmitter? A simple type of transport that we've already talked about. Vesicles merge up, fuse, plasma membrane, dump out contents into the extracellular space. Exocytosis, that's it. Dump, dump, dump. Oh, I don't have, I'll stick to brown. Dumps right into the little synaptic clefts right here. They're stored in these synaptic vesicles, and they merge with the plasma membrane and dump out into that space. And there's another downstream cell right here, either a neuron or a muscle, and it acts on a receptor that's specific for that neurotransmitter. So the chemical signaling between neurons is the neurotransmitters. The way that neurons and muscles communicate or talk, they fire an action potential down their cell bodies or down their axon or throughout the muscle fiber. But how they send that signal to the next chain in the pathway is via neurotransmitters. So right now we're talking about resting membrane potential, where it's sitting. If it gets a stimulus or it's going to fire, now we're going to talk about what zips down the axon to allow this communication to happen. Does that make sense? Okay. I feel like a lot of stuff is super interesting, but when I first learned it, it was very confusing. Like it was very sort of mathy, and everything seemed so abstract. Swivel back, or no? Are we good? Okay, so that's our little neuron we're going to add to that, okay? So it occurs in limited areas where ion channels are clustered on the plasma membrane. That's where current flow is going to be able to happen. Okay, so changes in membrane potential, this gets us to the firing. How does a muscle cell or a neuron fire? And when I say action potential, or when I say impulse or fire, all the same thing, okay? As a physiologist, I use them interchangeably, they're all the same thing. So at rest, the neuron is considered polarized. These are some different terms we're going to use. If you are a polarizing person, I know some. That's not funny either, sorry. If you are a polarizing person, what does that mean? What does that mean? Polarizing, you make things go in very different directions, right? Or you go against all kinds of stuff, or you make people go in other directions. It's either love you or hate you sometimes, right? So that means very opposite ends. The cell sits at an opposite end. It sits at negative, very negative. So it starts polarized. Okay, so these are the terms we're going to have to learn. When the membrane potential inside the cell starts to increase or become more positive, aka positive charges start coming into the cell, sodium channels start opening, start coming into the cell, that causes a term that we call depolarization. Well, if I'm polarized to start with, I'm very negative, and I get depolarized, what does that mean?
More positive.
More positive. Less negative, more positive, right? Same thing. So I start to go up. I start to depolarize. A return to resting potential, if I go up and I get more depolarized, and then it returns closer to resting, I'm repolarizing. I'm going back to negative. Does this make sense?
Yeah.
Okay. Repolarization. When the membrane potential inside the cell decreases or becomes even more negative than where it started, this makes perfect sense, right? Hyperpolarization. So I'm gonna add the sweeps of what an action potential actually looks like on here, and I'll stick to, I guess, blue, and we'll add to this. It will go up, reach a critical level, fly up, come back down, lower and more negative than it started, and then go back to RMP, okay? So draw that, and we're gonna add to it. So if I label these, I will say that this state right here is what? Based on the terms I just went over.
Polarized.
Cell starts polarized. Typical neuron starts about minus 70. When this is happening, what is all that? It is depolarization or depolarizing, okay? When I'm over here, repolarization. And what about when I undershoot and I go more negative than when I started for that cell? Hyperpolarization. Okay? Yes? Okay. That's it. That's what an action potential looks like. Okay? So then we're going to go in and go over the mechanics of exactly how that's happening. Okay? The different ion channels that are operating. So we can measure those real easy. Oscilloscope, it's not real easy. It's very technically challenging, expensive, and difficult. But we get this measurement, recording electrodes, we can measure that charge. So cell is sitting at about minus 70. Positive charge starts to come in the cell, and we can do that. We can inject positive charge electrically and stimulate that neuron, or we can put neurotransmitter that we know opens positive ion channels and allows sodium to rush in, and that will cause this depolarization. So we can put on a stimulus manually, or we can put on like neurotransmitter, or watch neurons in connection talking to each other, right, releasing chemical, and we can see that happen. Now the other opposing side of this is that if we inject negative charge, or we allow positive charge to leave the cell, or we put on a neurotransmitter that causes either of those two things, positive charge to leave, negative charge to enter, you will drop the membrane potential more negative. Hence, you will hyperpolarize that cell. So the two terms we use for this in biology are a depolarizing or excitatory stimulus, or a hyperpolarizing or inhibitory stimulus. The reason this is inhibitory, if a cell is just resting and it goes zoop, because you are getting further away from firing an impulse or an action potential. If I go up, I'm getting closer to actually make that happen. If I go further down, more negative, I'm getting more polarized. That's going to take a lot to get me to that place to fire an action potential. Okay? So these are some sort of principles and terms that we need to sort of understand going through action potential. Depolarization happens when positive ions enter the cell, and it's usually sodium. So upstream, now we have to add onto this, there are synapses coming from upstream neurons, sometimes multiple from like the same or multiple different neurons, sometimes on the cell body, sometimes out on the dendrites, and at these locations, they're like these locations. Oh, thank you, swivel. Okay, perfect. At these locations here, these synapses, very similar to the synapses down here, right? So they're releasing neurotransmitter. If they get an action potential and they fire, they're releasing neurotransmitter. Okay, so neurotransmitter, depending if they're activated, right, they're releasing neurotransmitter. So this neurotransmitter can bind to a receptor and can either cause opening of sodium channels, and if that happens, what happens to all this area of the neuron? If sodium channels open by that neurotransmitter that's activating this neuron, what happens?
Depolarization.
Changes the sodium ions. Where's sodium going to go? Inside. So you're going to start to get a sum of positive charges, because there's ion channels out here as well, okay? And there's receptors that respond to that neurotransmitter out here. So if you get enough stimuli, enough activation, you get a change in membrane potential that starts to become depolarized, starts to become very positive, okay? So that actually takes the cell closer to firing. Now the key to firing comes at the axon hillock. If it reaches there, the hillock or neck of the soma, or the top of the axon, that's actually what's going to determine whether this happens or not, whether it fires an action potential, okay? So these are the upstream stimuli, what's happening, what ion channels are opening, what's affecting the membrane potential. And if it reaches this sort of gatekeeper right here, this axon hillock, that determines whether that neuron is actually gonna fire an impulse, or whether it's gonna go the other way, and it's gonna hyperpolarize. So if something like a chloride channel, one of these neurotransmitters open chloride channels. Chloride channels, I haven't talked about chloride too much, but it's similar to sodium, high on the outside. Just think of those NaCl, they kind of go together, right? So chloride is high on the outside. If you open a chloride channel, where would chloride go? If this neurotransmitter binds onto a receptor, and that receptor was a chloride ion channel, because some neurons actually silence other neurons. Some turn them on, some turn them off, right? It's excitatory and inhibitory. Where would chloride go? Chloride, I'll just do a demonstration here. Chloride is very high on the outside, and it's very low on the inside. If I open chloride channels, where chloride can go? Inside. Okay, well, chloride's negative, right? It's a negative charge. What's that going to do to the membrane potential in here now? Make it negative. Where's it going to go? Is it going to hyperpolarize, or is it going to depolarize? It's going to hyperpolarize. Is that further away from firing? Yes, it is. So a chloride ion channel will actually make that neuron go away from firing. It'll silence it. It'll inhibit it. This is how different neurotransmitters in the brain and in the body can turn on or off other neurons in the chain. Believe it or not, there's many that are inhibitory that say, be quiet, don't activate, don't do anything. Motor control is all about that. You're turning off certain muscles and you're turning on other muscles. So this gating and whether it causes, this would cause hyperpolarization. And when we say hyperpolarization, we say this is inhibitory. This is going to shut down potentially that neuron's ability to fire an action potential. So if I go forward, hyperpolarization occurs when positive ions either leave the cell, if it's a potassium ion channel that gets open, or when negative ions like chloride enter the cell, if it's chloride ion channel. And I realize this gets confusing because you're like, oh my God, chloride, sodium, potassium. Neurotransmitters, there's hundreds of them. Dozens of major ones that operate in the brain. And they act on different pathways. They act on different channels or receptors. So they are affecting neurons in various different ways. Okay, so that upstream part is going to determine where this or this happens, when this or this happens, or how many stimuli are coming in, how many neurotransmitters are affecting that cell. Yeah?
Do ions like ever neutralize each other if there's like plus and minus? Then
Sometimes, like some gates will open and sodium and potassium can both go through. But usually one ion will win out based on its electrochemical gradient. So we'll see acetylcholine is a neurotransmitter that affects skeletal muscle, and it's in the brain in certain areas of the CNS. And that acetylcholine neurotransmitter binds onto its receptor. Its receptor is an ion channel, and it gates sodium and potassium. But more sodium comes in than potassium leaves. So it still ends up causing a positive charge and depolarizing your muscle. That's what actually allows you to move all your muscle and function. Use your skeletal muscles. Swivel, can we get a swivel? Back, sorry. Yeah, so for some of these I'll have to back it up a little bit when I do so I can get both sides. Okay, and that's why I like it when it's selfie mode, because I can see exactly and I can judge. But depolarization we say is excitatory then, right? Hyperpolarization we say is inhibitory. Okay, so just take a second, we'll do this little group share. You can work with people next to you.